On this worksheet, we're going to be drawing a whole bunch of E1 mechanism reactions. So for these reactions, with the E1 reaction, the first thing that we want to do is identify the carbon that's holding the leaving group. Double check to make sure that that carbon is actually secondary or tertiary and capable of undergoing elimination, and then just get rid of the leaving group and form a carbocation. That is going to look like this. Now, once we get our carbocation formed, we want to think about rearrangement. This is a secondary carbocation, and if we rearrange, we can get it to be a tertiary carbocation. Because the problem, the worksheet is asking to show at least one mechanism, that's why I'm taking the time to draw this mechanism out. So here we get to the tertiary carbon. Now, once we've got that tertiary carbon identified, elimination can take place between it and any carbon atom that is attached to it, any one of those. So we only need to draw the mechanism for one of these. I'm just going to choose the carbon atom right here. Our base, which is methanol, MEOH, the lone pair of electrons on the oxygen are going to grab one of those hydrogen atoms and then move the carbon-hydrogen electrons in to form that double bond. And that's going to give us this product right here. Now, without drawing the mechanism, it's also possible for us to form a double bond in this location, which would give us this product right here. And it's also possible for us to form a double bond in this location, which is going to give us this guy right here. Now with E2 and also with E1, once you've drawn a whole bunch of products, it is going to be important for you to go back and double check all of them. Make sure that you are drawing all of the cis-trans isomers. So every time you draw a product, you want to ask yourself, oh, is there a cis or a trans isomer to that? There's not in this case. There's not in any of these ones. Another thing that you want to do is make sure that you haven't drawn any identical products. These two products are exactly the same thing, which means that it would be incorrect for us to draw both of them. We only need to draw one of them. So those are the two products of this two elimination products of this reaction. Here is our next reaction. We'll go ahead and begin by protonating the oxygen so that it can become a good leaving group. And that's going to give us an OH2. The leaving group is going to leave, and that will give us this carbocation. That is a tertiary carbocation, which means it's not going to undergo any further rearrangement. Double bond can be formed between that carbocation and any carbon atom that is attached to it. So I'll go ahead and just start out here. It looks like probably the base we're going to be using is the chloride ion that's left over from the deprotonation. Not the best base in the world, but that's what we have on this worksheet. And so that will give us this particular product. It's also possible for us to do elimination out here on the end, so that would look like that. And it's possible for us to do elimination right here, which looks like this. And then after we get all those drawn, remember we want to ask ourselves, is there cis or trans? None of these have cis or trans isomers. And are any of these products identical? These two guys are identical, which means we don't want to draw both of them, just draw one of them. Here is our next one. This time I'm not going to draw a mechanism. Here's our carbon with the leaving group, and we can eliminate between any carbon that's attached to it. Oh, actually, you know what? We need to be a little bit careful. Even if we're not drawing the mechanism, first thing that we should do is just sketch that carbocation. Visually look at the carbocation, make sure that it is appropriate. That's a secondary carbocation, but there's no way to make it any better than that, so we're going to have to work with it. And then once we get that carbocation as good as it can be, we could do elimination between the carbocation carbon and any carbon that's attached to it. So I'm showing elimination in this spot and then also showing elimination in this spot. These two products, this guy right here is trans, and that means it has a cis isomer right there. None of these products are identical, so those are the three products for this reaction. And here's this one. So let's begin by imagining what the carbocation looks like. That OH group is going to leave. We are going to have to protonate it first, turn it into a good leaving group, but then it goes away and gives us this carbocation. This is a secondary carbocation, but It's a secondary benzylic. It's a secondary carbocation that's directly adjacent to a benzene ring, which means it's resonance stabilized. And secondary benzylic carbocations are extra stable. So even though it is only a secondary carbocation, this thing is not going to want to rearrange out here to the tertiary position. It's going to stay right here. So the secondary benzylic is just as good as a tertiary carbocation, no rearrangement. So that means we're going to form our double bond right here. Our double bond is going to form between this guy and the attached carbon. We can't form a double bond in this spot. This carbon atom already has 4 bonds. We can't give it another bond. That would give it 5. So we're only going to form a double bond out here. Remember, we want to ask ourselves, the terms cis and trans don't really apply here, but same concept. We want to draw both of those isomers like that. And I think we've got another page with some more. Yes, we do. So here's another one. Now, these are cyclics, and you might be remembering E2 and kind of panicking like, oh my gosh, there's a lot involved in this. Not the case with E1. The E1 reaction is very simple. So our first job is going to be to imagine that carbocation. When we lose the bromine, we're going to have a carbocation right there. When we lose the bromine, we also lose this stereochemistry. This carbon atom is no longer chiral because it only has 3 bonds. So that methyl group doesn't make sense to draw on a wedge anymore. This is a tertiary carbon, so it's not going to need to rearrange to turn itself into a better carbon. Elimination could take place between any of the carbon atoms that are bonded to that carbocation. So one option would be for the double bond to go right here outside of the ring. Another option would be for the double bond to go to the right side. And then another option would be for the double bond to go towards that second methyl group. If it does that, if the double bond goes here, this carbon atom is no longer chiral, which means we don't draw the methyl group on a wedge anymore, just like that. And we have one more of these. Let's start by getting rid of that leaving group and imagining our carbocation. Looks like that. Now that's a secondary carbocation, and we can rearrange it to turn it into a tertiary carbocation. And notice that nothing's happening with the stereochemistry for that tert-butyl group because no chemistry is happening on that part of the molecule. Nothing is changing here. So when I turn this into a carbocation, this carbon is no longer chiral, which means it doesn't make sense to use a wedge anymore. It's just a straight line. And then here's our carbocation, and elimination can take place in any of those 3 positions. So that means we're going to have 3 different products. We're going to have the double bond coming out of the ring. We are also going to have the double bond going towards that tert-butyl group. And we will have the double bond going up towards the top of the ring in terms of like how I've drawn it, upwards like that. Those are the 3 products for this reaction.